did last year in Europe. And that was using machine learning to predict fire spread and fire dynamics. So before we get into anything too much, I just want to talk a little bit about the methods of the overall project. So as we move forward, you kind of had some background knowledge. So this fire dynamic to the right here you can see. So you just have the meters and then the spread over time. So you can see that the black part is where the fire started from, and then as time progressed, it just kind of spread out. And to predict this model, I used a MATLAB code as kind of a basis. And a professor in my department already developed the MATLAB code, and it had already been proven to be accurate. So we used that as our training and test model for the machine learning code. To be able to run the MATLAB files, I submitted a job to the SSH, or using an SSH, I submitted a job to the RCC. And then the percentages that I decided to use for the machine learning model was 85 for training the model and 15 to test the model after it had already been trained. And then to kind of give you a little bit of an idea of what the machine or the MATLAB model or the physics-based model looked like, you can see here it kind of spreading. And then on this bottom little table is the parameters that were set for this specific model. And then since we're kind of on a time crunch, I think you kind of get the idea. And then here's just a different origin starting point. So it's kind of like a V shape, where the other one was like a straight line. And then the wind speed and sync terms and stuff is a little bit different as well. And then to the left is just the initial starting spot. Okay, so I just kind of gave like a little bit of preview of it, but the input parameters for this is going to be the background wind speed, the sink strength, which is basically just how much of the heat is being absorbed into the environment, the vorticity, and then the flame out time, ignition probability, and ignition pattern field. So that's just basically the odds that the fire will move to the pixel that it's next to, and then the starting location. And then the output is that first arrival time map that I was talking about previously. So there's just kind of like an easier way of looking at it. You have the map to the right and then all the inputs. So this gives you an idea, like a more like quantitative approach to the inputs. So in the parentheses is like the different options that we had for the model. So just for example, with the wind speed, it was either 2 meters per second or 8 meters per second. And then the flame out time, so how long the flame would last after it already started burning, was 9, 12, 15, etc. And then once again, I don't know if I commented on the specific samples, but it was 4,250 and 750 to make the percentages. And then for the ignition, the starting location, we had it all as like a straight line, and then just the angle from that line is how we had the starting location for the fire. We don't have like a whole bunch of time to go into like the in-depth model and stuff, but like if you're really into like the super technical side of the model, this will kind of give you an idea of that. But basically there's a 160 by 160 by 6 image. So the 6 is for the 6 different parameters that I mentioned before. And then the 160 by 160 is just the map that it's starting on. So even though it's on at 200, it's actually really only going to like here. Yeah, and then the output is a 160 by 160 by 1, which is just like, basically the 2-dimensional image. And then now kind of getting into like how effective the model was and stuff like that, we can look at the mean squared error over the number of epochs. So as you can see, the model was, pretty accurate and stuff. We got that nice little curve we want, and then the number of epochs was obviously a good number. And while this is good and stuff, I always think like a visual example is a little bit more, because these are all just kind of like arbitrary numbers. So if we look to the left here, we have the numerical prediction on the physics model, and then to the right is the machine learning output. So you can see it's obviously pretty similar. And then here's just like a different starting location to try to prove that it wasn't like, it's not just that one example that happened to work out that way. Like they all are pretty accurate. So at this point, you might be wondering, okay, well, you have this physics-based model that can run on MATLAB that can predict a fire, great. So what's the point of using like machine learning or convolutional neural network to predict? Because you can just use the physics model for everything. And the biggest reason for that is just the time. So while it might take a second to train the machine learning model, so that took about 910 seconds. And all these times are kind of approximate because as it goes from from different time to time, it's going to vary. But it was like roughly 910 seconds, depending on like the batch size and stuff like that. But after the model was trained, the time difference was very significant. For the convolutional neural network, it could do 1,500 samples in less than a second, while the physics-based model took like 196 minutes to do 100. So you could see if you're trying to predict how fire will spread in like a wildfire, or you need to make an evacuation procedure or anything like that, that just might not be enough time for something like this, where the machine learning model could quickly inform decisions. Yeah, that's all I have. Thank you so much for listening to me. I'd be remiss if I didn't mention my research mentor who helped me with this project. She's now at the University of Kansas, but Dr. Shin Tong helped me a lot with this. And yeah, go Knowles.